Today we'll learn more about truth tables and about how we use them to determine whether an argument is valid or not. Let's do a brief review of truth tables and their construction. Remember that what a truth table does is, for a given set of sentences, to list all the possible ways in which we could assign truth values to the sentences. For instance, for a single sentence, there are only two ways in which it may turn out. It's either true or false, and each row corresponds to each possibility. If we add another sentence, we see that the number of possibilities is exactly 4. It could be that both are true, it could be that P is true and Q is false, it could be that Q is true and P is false, or it could be that both are false. In general, the number of rows in a truth table depends on the number of simple or atomic sentences. So, with 2 sentences, P and Q, we have 4 rows. And with 3 sentences, how many rows will we have? We're going to have 8 rows. With 4 sentences, we have 16 rows, and so on. The rule is that the number of rows is 2 to the power of n, where n is the number of sentence letters or atomic sentences, right? So if you have one sentence, it's going to be 2 to the power of 1, and if you have 2 sentence letters, it's going to be 2 to the power of 2, that is 4. If you have 3, it's 2 to the power of 3, that is 8, and so on. It's always useful to keep some order when you are building your truth table. For instance, the common method is this. Take the first column. Well, the first half are going to be true, and the second half of the rows are going to be false. Now, the next one, you're going to have that the first quarter are going to receive true. The second quarter are going to receive false. The third quarter are going to receive true, and then the fourth quarter is going to be false. And then the same principle goes for the third column if there is 1, right? 1/8 is going to be true, and then 1/8 is going to be false, right? Etc. Now, let us remind ourselves of how truth tables allow us to determine validity. Take this argument, for example. First premise, Al sings or dances. Second premise, Al doesn't sing, and he doesn't jump either. And then the conclusion is, Al dances. Also, you have this key. Instead of Al sings, you will use the letter S. Instead of Al dances, we use the letter D. And instead of Al jumps, we use J. With these abbreviations, our argument is SVD. Then the second premise is tilde S ampersand tilde J. The conclusion is D. Moreover, our argument that appears on the right is a substitution instance of the argument form to the left. And so we can see that we obtain the argument from the argument form by uniform substitutions. So if we substitute in the argument form P with S, Q with D, and R with J, we get exactly our argument. So now let's use the truth table to see whether the argument form in question is valid. We could do it directly with the letters of the argument, but this time we're going to do it with the argument form. And so we had 3 atomic sentences, P, Q, and R. That means that we have 8 rows. Now here we just have a display of the first premise of the argument, of the second premise, and the conclusion. So you see that each of them gets 1 column. Now remember that an argument is valid if and only if it's impossible for the premises to be true and the conclusion to be false, right? And an argument is invalid if such a thing is possible. That is, an argument is invalid if it has a counterexample, where a counterexample is a case where the premises are true and the conclusion is false at the same time. So in order to determine whether an argument is invalid, which is what we do, we first see if there is a row in which all of the premises are true. And we see that row 6 has both premises true. Now we see which value the conclusion has at this row. and we see that it's true. So this row is not a counterexample, right? It doesn't show the invalidity of the argument. Also, notice that there is no other row in which both premises are true. So we can conclude that there are no counterexamples, and thus this argument is valid. Now let's consider a different argument. The first premise is Al sings or dances. The second premise is either Al doesn't sing or he doesn't jump. The conclusion is Al dances. Using the same abbreviations as in the previous example, we see that the argument is S or D, not S or not J, therefore D. Our argument is a substitution instance of the argument form to the right. That is, it is a substitution instance of P or Q, not P or not R, therefore Q. So you can do the substitutions if you want to convince yourself of the truth of this. And now we proceed exactly as in the previous case. So we have 8 rows, and then we have a column corresponding to premise 1, and a column corresponding to premise 2, and a column corresponding to the conclusion. And so first, we look for rows in which all the premises are true. So we have that our second row, our fourth row, our fifth row, and our sixth row have all of the premises true. Now the question is the conclusion false at any of these rows? Well, let's look at the second row. The premises are true, but also the conclusion is true, so that's okay. It doesn't constitute a counterexample. But if we consider the fourth row, we see that although the premises are true, the conclusion is false. So this constitutes a counterexample to the argument. We can't stop there. Why? Because it is enough that there is one row in which the premises are true and the conclusion is false to declare the argument invalid, right? And so this argument is invalid. And why? Because there is at least one row in which the premises all get T's and the conclusion gets an F. If you feel that you have a good grasp of how to use truth tables to determine validity, then you don't need to watch the rest of this video. You can stop now. But if you had trouble following our previous examples, or would like to have a more thorough review of all the steps involved, then keep watching. So let's see whether this argument is valid. So the first premise is not P or Q, the second premise is P, and the conclusion is Q. So if we want to use truth tables to see whether the argument is valid, the first step is to draw the table itself. And so this table is going to have a column for each of the atomic or simple sentences, and it's going to have, of course, the right number of rows. So if the only atomic sentences that were involved in this argument form were P and Q, and when we have 2 atomic sentences, then we're going to have 4 rows. The second step consists in drawing the columns corresponding to the premises and the conclusion. Now, if the premises or the conclusion themselves are conjunctions or disjunctions, then you do a column for each of the components, and so on. And that means you should start from the smallest sentences. We'll see what this means in a second. So our first premise is not P or Q. So eventually we want to have a column which is devoted to that premise. But notice that this is a compound sentence, right? It is a disjunction. And it is a disjunction whose left disjunct is a negated sentence. This is evident from a decomposition of the sentence. You see that not P or Q is formed by joining not P and Q by means of the V. Furthermore, not P is formed by adding a tilde to P. So the way in which this sentence is built from the bottom up, right, from the atomic sentences by the addition of connectives, well, this way is going to tell us how we're going to work our way towards the column that corresponds to not P or Q. So we know that we already have the truth values for P and for Q, right? Because those are the first 2 columns. Now we see that the smallest of the non-atomic sentences that compose not P or Q is not P, right? And we don't have a column for that yet. So we're going to start with a column for not P. And here it is. And since we have a column for not P and for Q, which are the median components of not P or Q, we are ready to build our column for not P or Q. And we can identify not P or Q as premise 1. So this column is going to correspond to premise 1. So our second premise is P, and our conclusion is Q. And so we're adding columns for them just for clarity, but really we don't need them because we already have a column for P and another one for Q to the left. But again, just to make things as clear as possible, we are adding a column for P in its capacity as the second premise and for Q as the conclusion. Now that we have our columns and we have identified which one corresponds to the premises and to the conclusion, the third step is to fill the table with truth values, that is, with T's or F's. We know how to fill the first two columns. In the case of P, the first half of the rows gets T's and the next half gets F's. In the case of Q, the first quarter gets T, the second quarter gets F, then again we have T and F. Now we fill the column corresponding to not P, which is basically the opposite of P, right? So if P has a T, then not P is going to have an F, and vice versa. The next step is to fill the column for not P or Q. Now here, the only columns that are going to be relevant are going to be the second and the third, right? Because those are the column that corresponds to the components of not P or Q. So the column corresponding to P is going to be relevant, right? So just pay attention to the column corresponding to Q and that to not P. And so since not P or Q, well, is a disjunction, we know that this sentence is going to be true whenever at least one of the disjuncts is true, right? It is only false when both disjuncts are false. It's true otherwise. And so in the first row, we have true and false, and so we have T, we have true. In the second row, we have false for both sentences, and so we have F. In the third one, we have true and true, and so we have true. And in the last row, we have false and true, which again gives us true. Finally, for the last two columns, we simply copy the contents of the first two columns. The next step is to find rows where all the premises are true. And we see that there is only one row where this happens, which is the first row, right? Both premise 1 and premise 2 get T's. In all the other rows, at least one of them gets F's. The next step is to take that row and determine whether the conclusion is true or false at that row. And so we see that the conclusion is true. So this is not a row in which the premises are true while the conclusion is false. The next step is simply to apply the definition of validity to what we found in the truth table. Remember that an argument is valid just when it is impossible for the premises to be true and the conclusion to be false, right? And therefore, an argument is invalid when it is possible for the premises to be true and the conclusion to be false. That means that an argument that has counterexamples. In truth tables, our talk of possibilities turns into talk about rows, right? Each row is a possibility. And so an argument is invalid, right, if its truth table has at least one row in which all of the premises are true, but the conclusion is false. That counts as a counterexample to the validity of the argument or the argument form, right? And so we have to look back at our table and then ask, is there at least one row in which all the premises are true and also the conclusion is false, right? If the answer is yes, that means that the argument or argument form has counterexamples. So the argument is invalid. In contrast, if the answer is no, then that means that the argument has no counterexamples. And so the argument or argument form is valid. In the case of the argument we were evaluating, we saw that there was no row in which all the premises were true, but the conclusion was false. So that means that the argument was valid. So here's a summary of the steps we have identified for determining validity by means of truth tables. And the first group of steps correspond to the construction of the truth table itself. So the first one is to draw the table, beginning with the columns corresponding to the atomic sentences. In the case we were examining, we only had two, P and Q. But you could also have P and R, Q and R, or P, Q and R, etc. The second step is to draw the column corresponding to the premises and the conclusion. And the third step is to add the truth values. The truth values for the atomic sentences are just gonna be by the procedure that we outlined earlier, right? So the leftmost column is gonna have the first half true and the second half false, and then the second column is going to have a quarter true, quarter false, quarter true, quarter false, so on and so forth, right? And for non-atomic sentences, the values are going to depend on the truth table of the connective, right, that is involved. So if we have not P, then we're going to fill that column by looking at P and simply inverting the values that are in P. And if we have P and Q, then we apply the truth table of the conjunction, namely that P and Q is only going to be true in those cases in which P is true and Q is true. So the next group of steps have to do with the determination of validity itself once we have our truth table. So step 4 is to try to find rows where all premises are true. And then check whether, in step 5, we check whether any of the rows you identify in 4 has F in the column corresponding to the conclusion. The next step, step 6, is to ask yourself, well, did you find at least one row where all the premises are true and the conclusion is false? If you did find such a row, then the argument is invalid. If you didn't, then the argument is valid. Now let's apply the procedure to this second argument form. We have the first premise is not P or Q. The second premise is P, and the conclusion is not Q. Then we build our truth table, including the columns corresponding to the premise 1 and premise 2 and the conclusion, and with the truth values. Then we look for rows where all the premises are true, and we see that the first one is such a row. Then we determine the truth value of the conclusion in that row, and we see that it is false. So that means that we found at least one row in which all the premises are true and the conclusion was false. That was our first row. That means that the argument form is invalid. And here we see the first row, which constitutes a counterexample to the argument form, and therefore shows that it is invalid. Okay, this is all for now.